So in this session, I will be discussing about RIS for 6G. What is the current status of RIS in the standardization, mainly in the standardization and 6G systems. So I'll be briefly discussing about 3GB standardization and RIS in 3GB releases. Then discuss about RIS channel modeling. Then I will give a tutorial on how to perform some experiment on RIS using Gradle platform. So there are two main organizations involved in the standardization, global standardization. One is ITU and another is 3GPP. So it is the International Telecommunication Union. All government bodies, like particularly in India, TRI is part of ITU. Almost all countries in the world are part of ITU. So 3GPP is the private organization. All cell phone manufacturers, chip manufacturers, cell phone operators, all are part of 3GPP. So 3GPP is the organization that develop and maintain the standards. For example, GSM, that is 2G, UMTS 3G, LTE 4G, and 5G NR, 5G near radio, that is for 5G. All are developed by 3GPP and maintained by the system, the 3GPP only. So basically, there are 7 regional organization partners in 3GPP. Our TSDSI. One second. So we have TSDSI, Telecommunication Standards and Development Society India. It's a part of 3GPP. So if we want to make any contribution towards standard, we have to approach through TSDSI. So TSDSI is the bridge between us and the 3GPP in India. Similarly, in different regions, they have a different organization. In Europe, we have ETSI, in USA and ATSI and such things. Okay, so before developing any standard, there are 3 stages. One is vision statement, vision, development, and deployment. We can just consider. So this figure shows the from 1995 to 2020 the progress of the standardization process. If you think of 4G, we have vision statement was defined in 2003. It took 3 years to make the vision statement. Then from 2003 to 12, they made the standard. But development happened for 9 years. Then 2012 onwards, globally we started deploying the 4G networks. Similarly, for 5G, vision statement from 2012 to 15. Then within 5 years, 2015 to 20, they developed the standard. By 2020 end, we started enjoying the 5G services globally. Okay. So for us, it's a 2G, 3G, 4G like that. For us, for 3GPP, it is a releases. For example, in 2014 they had 13. So in 2010 like that, they had release 10, 11 like that. So 10, 11 is called 4G. 12, 13 are 4G, 4G advanced like that. So currently we are having release 15 and 16. They are 5G. Similarly, when it becomes release 19 or 20, it will become 6G. So we can expect that around 2030 we will have 6G systems. So this is the I mentioned about the. So is my PPT visible to you? Hello?
Yes, sir, it's visible.
Okay. Someone is asking it's not visible. Yeah. Okay. So here I mentioned about the vision statement. No? So this is the recommendation from ITU. Within the next 10 years, this will be the traffic demand. Accordingly, we have to make the system like that. So they will put up the requirements in terms of throughput, latency, and reliability, all those stuffs. In so we can see that this is for the 5G. They made it data rate is would be 20 Gbps per cell phone tower like that. The latency 4 milliseconds for broadband communication and 1 millisecond for reliable low latency communication services. So constant density will be 1 million devices per kilometer square in the case of IoT and vehicle connections. The reliability should be almost close to 100% is a requirement. So this is the kind of vision statement from the IT. So based on this requirement, 3GP will develop the system for next 5-10 years. That is a procedure development. So if you think of the 3 releases from it started with the phase 1 in GSM 1992, then it started uh, 3G in 2000, around 2000s, release 99, then release 10 become LTE 4G 2011. In 2016-17, we started moving towards 5G. Release 15 is 2018, fully completed. So we can see that release 15, 16, 17, 18 have different features. For example, release 15 have support for vehicle-to-X communication, and release 17 is having additional like non-directional communication, like a satellite integration, IoT integration, all those stuff. So support for uncrewed aerial systems. Drones and all is part of 5G now. They started coming into release 17. So in release 18 is they're primarily focusing on, so release 18 will be over by 2025. They're primarily focusing on AI, ML, and virtual reality applications, immersive communications. They are in terms of applications and the usage of tools from machine learning and AI. They are going to come into the release 18. This focus thing. So till this point, there is no information about RIS. It's maybe RIS may come in release 19, 20, 21 like that. So this is the way it goes like that. So whenever the RIS research is matured and the hardware implementation is done and so proof of concept is achieved, then they will implement it in the standard. So in this, still in this, it is under the research. So this is basically release 18 timeline. So by 2025, it shows. Is my screen visible now?
You can continue.
Yeah. Okay. So release from till 2025 it is release 18 only, and release 19 will start from 2025 6 like that. Then we can just see the main features of release 19. Relay communication and AI model transfer, all those things part of 19. So when we will achieve the 6G communication system, this is the timeline for 6G. The figure shows from 2000 to 2030, and particularly for IMT 2030. IMT 2030 is for 6G. So IMT 2000 is 3G. IMT 2020 is for 5G. IMT 2030 is 6G. So the framework is being developed as of now. So from last 3 years, at the end of 2024, they will be making their recommendations, the vision statement and all. The requirements will be put up in at the end of 2026. The standard development will happen from 2027 to 2030. So 3 years, it's much faster than 5G. It will happen for 3 years. Then enhancements will come into picture. So we can expect after 2027. Okay. This is the overall standardization process. So as of now, there is no mention about RIS such thing in 3GB releases. It will come most probably in 2020s. After the requirement is put up, it may be coming in 2027 like that. So, but before that, the academic community is going to develop all the channel modeling, capacity analysis, all those stuffs. And as a part of standardization, there's one more thing. The channel modeling is the main important thing. Before, so I have mentioned about this standard development and standard enhancement deployment, right? System development deployment 2030. But standard development will happen from 2027 to 30. So in the what they do will actually they do. They are the companies, all the private 3GP partnership project partners will do is they will simulate the cellular architecture. So they will put up the cell for cells, user base stations, user equipments, antenna height, all the antenna pattern, everything. They will do the simulation of the environment. For the MIMO system, they will generate the MIMO channel modeling, all those stuff. So that will be given in some report form. So this will be given by the ITU. So ITU for 4G, we have ITU-R M2135. It was released in 2009. So based on this document only, the companies will incorporate the changes and propose the 4G or 5G systems. Similarly, for 5G, this number is M2412. It is released in 2017. Based on that only, they will finalize the standard. Similarly, for 6G, similar report will be coming. Probably by 25 or 26 like that. So what is the content of this report? So actually I have shared one Google Drive link with all of you. In the Google Drive link, so I shared all the files. Okay, so including my slides, I have shared all the files. In that file folder, we can have we can see that 4G REP M2135 and 5G M2142. These are the two guidelines for performance evaluation of 4G and 5G. Similar documents will be there with the 6G also. So this is kind of around 150-page document it is for 4G and 5G. So this is for 4G. Just we will go through the how it looks like. So you can see that there is a left side. I'm moving it. It is evaluation methodology. The evaluation methodology. The system simulation procedure will be given. So in that you have to consider scenarios like you have to create a cell layout like this, and in the cell layout with 3 sectors each for each site. For different scenarios you have to generate this scenario and drop the users, multiple users, and perform the simulation. So each base station will have multiple antennas. Each equipment has fewer antennas, and interference, SNA calculation, all those things you have to do the analysis. So just to go through the tables and the contents, you will get the idea of what should be the transfer power of the base station, what should be the transfer of the user equipment, number of antennas at the base station, and mobile. What is minimum distance between the EU and the base station, all those stuff, or not, everything. What is the bandwidth used by the system, everything will be given. Then most importantly, what should be the user distribution? Random and uniform distribution. See, we can see the top portion. You can see the there are scenarios as well. Indoor hotspot, urban micro, urban macro, rural macro and suburban macro. So urban macro is suitable for metropolitan cities, Chennai, Mumbai, Bangalore kind of cities. Urban macro means suburban, outskirts of the cities. Rural means so some of you asked simulation tool is open source or not. Actually, uh, the simulation is done using C++ language in big servers. So each simulation will run for 1 week or 10 days like that. So continuously the simulation will run for suppose if you want to run 1 hour simulation, 1 hour suppose practically 1 hour is tower is running. For running the 1 hour system, we have to simulate for 7 days to 10 days. So they will be using big servers with the C++ language. So we can also develop the systems using Python or MATLAB also for our research. So, but the processing time will be bigger. If you want to do the full-fledged simulation, but for our academic research, we need to do the full-fledged simulation. For MIMO and all, we can do miniature level simulation that is suitable, good enough. So there are materials available also for open system level simulations available. There is something like a Sienna simulator, Vienna simulator. I will share the details. Maybe we can put it up in Google Drive also. So these are the parameters you have to consider. 50% usually being indoor, outdoor, all those stuff. User mobility model, at what speed they are moving, all those things. Okay, and so evaluation service profile, full buffer, best effort traffic model, all those things. So this is the antenna pattern you have to consider. So this is antenna orientation, all the stuff. So then most importantly, we have to build the channel model. So this is the overview. So two things you might have heard. The one is large scale fading and small scale fading. There are set of procedures and parameters given in the document. We have to follow as per the document. Then only we can comply with the 4G or 5G system. For path loss, for each scenario, individual hotspot, urban micro and all, we have path losses, path loss formulas. We have to use this path loss formula. This contains path loss, distance from path loss, shadow fading, all the parameters. Okay, we have to implement this and do the performance analysis. This is for large scale fading. For small scale fading, we have detailed procedure. So you can just see this, delay spread, angle of aperture, angle of derive, departure, and all those things. So setup, there are some small scale parameters. It contains a lot of parameters. You have to implement this. So finally, we will be getting this kind of H matrix. So in all the publications, we will be seeing that there is H matrix, y equal to H into X plus noise. The H is derived using this formula only. It contains polarization, small scale fading, antenna spacing, all those all the parameters. So this code for this is available in your Google Drive link. So I have kept for 5G UMI analysis model channel. So there are different scenarios like UMI, LOS also there, UMA, LOS, UMA, analysis, all those things are there, but I kept only one. So based on this, you can develop other systems also. So the different parameters you can see. See, but specific to particular scenario, EMI, SMA, and all those things. This is given for so this is the scenario for base station antennas to the user equipment. So there is a base station location and the user location. Then antenna position are known. From that, we will derive the other parameters. So now this is point to point base station to user equipment. Multiple base stations. Let's say there are 19 base stations and one user equipment. There are 19 links. So you have to generate that many. For example, in this particular. So for this particular maintenance layout, assume that there is a user at cell 3. So the user is getting signal from almost all sites. So there will be 19 interferences. So each base station has n number of antennas, right? So that many links we have n times 19 into 9 n times channel coefficients you have to generate and do the analysis. So this is the document I'm sharing with 4G. For 5G, M2412 is more or less same. The channel modeling is more or less same with additional, so small modification will be there. So same thing. In 5G, you had indoor hotspot A and B, and for UMA, A and B. UMI, A and B, something like that. So path of smart is more or less same. Small difference will be there. So what we can expect to 6G? 6G also will be similar kind of thing with additional details. Suppose if we are incorporating RIS into it, we have to consider that as one node. The number of elements going to be increased. The procedure remains same. So generating the small scale fading parameters remains same because we have to go find the position of the antennas at the base station, RIS, and the user equipment. We have to create the link. You have to generate instead of one channel. Now we have to create three channel coefficients. Base station to direct UE, base station to RIS, RIS to UE. So these three channel coefficients you have to generate. We follow the same procedure. Okay, so okay, so you got the I guess you got the rough idea how the things works. So this document is for 4G M2135 and M2412 is 5G. 6G also will be same. Why I'm saying if you compare 4G and 5G, the small scale fading procedure is same. The parameters are a little bit added. So same thing going to happen for 6G. Probably with the RIS and all, you'll be having one more additional panel kind of thing. With that, you have to get the additional coefficients. So suppose if you want to contribute to the standard, for 5G, for example, still the 5G is running, 5G enhancement is happening. You have to follow the document and propose the algorithms accordingly. As of now, what academic people are doing is that they assume that relay fading for generalized relay fading for performance evaluation. So it's not a we don't always get the relay fading. We get the Dyson fading with the different K factors and all. So we have to incorporate in this particular channel model. We will see that the K factors and all will be visible. So you can see the KR factors and all, they are coming from the relay fading Dyson channel modeling. So basically this kind of combination of Ryzen and the relay channel coefficients in 4G, both in 4G and 5G. Okay. So now what I'm going to do is, so I have taken one paper. I took the code from the authors and modified slightly to be used by other people as well. So I kept it on the Gaggle platform. You can also on the Google Drive link. So I kept two Python files. One is 5G UMI analysis channel model. From that you can generate the channel coefficients. And another file is end-to-end RIS G. So in this file, the implementation of the algorithm given in the paper is given. So this particular paper, end-to-end learning for RIS aided communication systems. Okay. So according to this paper, okay. So according to this paper, so mostly I'm following this paper and this one. So this is the typical scenario. So there is a base station on the top of the building, and there is user equipment and the vehicle. There is a panel for RIS. So the base station contains NT antennas. The user equipment contains NR antennas. The RIS has N antennas. So in this paper, they assume that NT is to be 8 and NR to be 2 and N could be 128 or 256. Okay. So what they have assumed is that they have assumed relay feeding. They did not consider the standard aspects because for academic obligations, we need usually people use relay feeding. So first, what I will do, I will show the code for implementing the algorithm given in the paper using Python language with the help of ATAL platform. Then I will explain about the channel modeling in how it happens in 5G. Then you will be able to integrate the 5G channel into this end-to-end RIS algorithm and get the new results. So basically, if there is a line of set link, the performance will be different. If it is NLOS, one line of set, the performance will be different. All these combinations we can try with the different scenarios. How it happens in indoor hotspot, how it happens in urban AOMI, urban micro, all those things. So this will be useful for if you are publishing paper with a different with the tag 5G 6G. So 6G is, as I mentioned, release 19 is going to have AI ML techniques in 6G. So release 19 is not 6G, but it's a bridge towards 6G. So probably release 2021 becomes 6G. So the initial steps are already taken care of in engine itself, release engine itself. So according to this particular paper, end-to-end learning for RI-centered communication systems, published in 2022. So what they assume is that the base station contains NT antennas, user equipment contains NR antennas, the RIS contains N antennas. So what they do is they do combined deep learning techniques at 3 stages. So typically when you do the downlink transmission from user equipment, base station to the user equipment, you do the pre-coding, right? So B1, B2, B3 as the bit stream, and we will do the modulation along with the pre-coding. So before pre-coding, we know the channel coefficients between the base station and so let's assume that in the absence of RIS, so there is a direct channel available H. So the base station will transmit the pilot symbols either in the downlink and uplink. So once typically in massive MIMO, the uplink pilot is much less complex. So from that, they will know channel coefficients, or CSI. Then station will do the pre-coding, right? This is a typical thing happens. So in this paper, what they do deep learning based neural network in three places. One is at the base station for calculating while doing the pre-coding, they do the DNN, apply DNN, and while demodeling the data at the receiver side, user equipment side, they are doing the DNN, two DNN, and third DNN for RIS, the coefficients for the each antenna element. So there are 3. So the channel between base station and RIS is G, between the RIS and the U is F, and directly from base to U is H. Okay. So these are the assumptions they make. So H, F, and G are estimated using RIS channel estimation method given in reference this reference. So 2 times scale channel estimation for reconfigurable intelligent surface area wireless combination. So they assumes that the base station knows G, H, and F. So based on that, they do the optimization at the base station side, because the base station has much more computational capability. It can do the processing. So yeah. So and one more thing is that the H and base station and the RIS are fixed locations, though the channel will be slowly moving because due to surrounding objects, moving vehicles and all, only it will going to change. Though it will be static for the long period of time. Compared to the channel H. H is going to change instantaneously, and the F also going to change instantaneously because of the movement of the vehicle or user equipment. If the person is moving by walkable speed, also channel is going to change frequently. So this base station to RIS link is kind of stable. Changing for a long period of time. The link between base and the UE and the RIS is going to change abruptly. This assumption they make. And so they apply deep learning techniques. I'm not going in details of that. So I will give the code. Then when we have a time, can have a look and understand it yourself. Otherwise, you can ask me. I will reply back. So WBS, theta, and W user. These are three coefficients. They are. So I hope all of you know about deep learning techniques for in general wireless and any other image processing and all. I hope you know the terms. W is the weight coefficients. W, theta, and W user. So WBS is the weight factor for the pre-coding matrix, the pre-coding side. W user is the weight coefficients for the demodulator, and theta is the weight coefficients for the RIS. So if you see the paper, it will be more clear. So this is the received signal at the user equipment. So Hx plus n plus f into theta multiplied with g and h. So from directly from base then plus through RIS link. So here what they are doing is that they are so at the receiver side we have to do this estimation remodulation. So there are different techniques like zero forcing, Rimami algorithms. You can use it for demodulating the received signal. So keep you into y. So now there are three terms. Q, the user is going to apply. So Q is user is going to apply the demodulation. Theta is from the RIS. So while doing the transmission from the base station, the base station will do the pre-coding. That is coming with the parameter P. So the problem is like minimizing these all the parameters P, Q. So minimizing the whole function with respect to P, Q, and theta. So in this particular paper, what they had assumed that the base station knows H, F, and G. Then it find out the coefficients for all these WBS, W user, and theta to minimize the bit error rate. Okay. So these are three parameters. They are coming from the deep neural network, WBS, theta, and W users. So these are available at the base station. Then the coefficients, the WBS is needed, only the WBS needed at the base station. Theta is needed at the RIS. W user is needed at the user equipment side. So what they assume is that the data is transmitted to the RIS via wire or wireless link. Because the RIS is in the fixed location, that can be connected via wire or wireless link. The data can be transmitted that way. So the W user is transmitted via wireless link. That it needs some additional control information. It requires some bandwidth, but you can do the quantization and all, you can transmit it. That is the assumption they make. So, in summary, the base station has much more computational capability. So it does calculate the WBS, theta, and W user. Then it transmit to the RIS, the theta, and the W user to the user equipment. So with this available information, the RIS applies its um, uh, the reflection coefficients and minimize the bit error rate. So the number of base stations is the parameter they have considered. Number of base stations as 8, and this one as 2. The number of RIS element is 128 or 256. So they assume fixed BS location at 0, -40, and RIS location 60, 10, and user location changing from 0 to 100. Every 10-meter steps, they are changing the user location. So in order to perform the experiment, you need to install, you need to have account in Gaggle platform, and you can use this particular code E2E So this code you have to upload, and then it will look like this. So this code also need some additional information that can be inputted as a data set. So the data set I made it public. We can click this button. After you can so if you open the Gaggle as a fresh, you will get dashboard like this. So here you have to click code and a new notebook. If you click new notebook, you will get this window. From that, we can import notebook. Import notebook. Go to browse files after downloading that from the Google Drive link. So E2E RISCG. Right? So this is the way to import a notebook. So you can change the file name. So you have to add input like this. So RIS, if you search for RIS 6G dataset, it will be appearing there. You can add it to your file. That's it. Then you have to click run all. So this code will implement the algorithm as given in this particular paper. So these are the parameters they have considered for deep neural network on the base station side, RIS and the user DNN. So I'll just give you some hint about what are the parameters they have considered. See this, you can see that that's a channel function. So channel data between RIS and user is generated using this combination. This particular one, the RIS to user means number of antennas they have considered. In this code is 1024. You can change it to 128 or 256 also. Transmit antenna, receive antenna, and the number of channel coefficients we need to have. And similarly, base station to RIS, 8 transmit antenna, 2 base RIS 1024 RIS antennas. Base station to user is 8 2 n by 2. So the user distance is given in this range. So if you give this way, it will create the values like 0 and 10, 20, 30, but like up to 100 will be the values. So 10 user locations are given. Each location again the analysis, performance analysis. So for training, you have to consider particular SNR. So so the idea is that you train the network with a particular SNR, and calculate the BL for different SNR values. For training, we use single SNR, and for actual transmission, the SNR may be different. So the SNR value that you are using for training, that also influence the accuracy of the result performance. So there are many parameters we have to. This is the example code that given. So we can tune many parameters over here: number of antennas, number of RIS antennas at the base station, user equipment, the distance between the base station and the RIS to user equipment. All those things you can change. So I'm not going into the detail, but this is the working code. So you write it yourself, and if you have a doubt, and you can ask me through email. I'll be happy to help. So once you run the code, it will generate output file over here. Output will be, see, if you run the code, it will take some more than 20 minutes. Let's see if it is running within before the session is over. Then I will show you. Here it will be there. Then you can download the code, download the data. So I have I ran it already. I kept the output file over here. So outputs to this is the one. So yesterday I generated it. It is available over here. You can have a look. And so this is the kind of figures you will get it. So the x-axis is the distance between the base station and the user. Because the base station and RIS location fixed. This is the distance between the base and the user equipment, right? So you can see that they show. I mean, they prove that with respect to the other works, their algorithm is performing better. So as I said, the particular training that you are making, that depends on the SNR, user location, many factors. So if the user location is different, you have to do the training again. So the training has to be online. If the user is fixed, if you do the training today, maybe you can use it tomorrow also. The channel is not changing much. Suppose we are showing indoor location, you have fixed transmitter, RIS, and the receiver. In this case, the channel is not going to change abruptly. So if you do the training once, that is good enough. We can use it for long period of time. But if it is outdoor scenario, you have to do the training online every time. So probably every few milliseconds or every second you have to do it. There is no other option. In outdoor scenario, it may be difficult because the channel is going to change abruptly, and the channel permissions has to be sent to the base station to do the operation. Okay. So if you want to incorporate, AML with respect to the in the physical layer in this way, so you will get this kind of graphs. So while writing the DN network, there will be a lot of iterations to get minimized VER. So you can see the progress like this. It will run for more than 10 minutes. Then you can see the results later on. It will be visible over here. See here. So the outputs are kept over here. Different scenarios. So you can download it. To understand the code better, the first level, with the default, you can run the code and get the result, and then try to change the parameters like user distance. User distance is there, but is location. So if you see the data set, there are multiple files in that. That's a channel generator. So in the channel generator code, so channel function is called from relay channel. So CG dot relay channel. CG is basically your channel generator. Channel generator is called as CG. From CG, you are calling the relay channel function. So you can change it to monogamy. So in this code, so channel function we have to passing the parameters, number of antennas and such things. So this is the code for generating relay spreading coefficients. You know that this is a simple way to generate relay coefficients. G plus J. I mean real part plus imaginary part with a certain normalization and all we get it. This is very simple for generating Rayleigh coefficients. So if you want to do it with a 5G channel or a 6G channel, so as of now, they are generating the channel coefficients using Rayleigh query, right? These are three lines focused on generating 38, 39, 40 has code for generating channel coefficients. So if you want to do it with the 5G or 6G, we have to replace these channel coefficients with this code. So this code is available in the Google Drive link. So you can just see the parameters. So from where I have taken, I will show you. So here you can see this, DS, delay spread, angle of departure spread, angle of arrival spread. There are many parameters, mu, sigma. So these are all are statistical parameters with following the distribution. A Gaussian, mostly in Gaussian distributed. This is the mean and this is the standard deviation. So these parameters we have taken and kept it over here. So we can, with respect to the document, you can refer this. So as I said, this is for UMI NLOS. If you want to do it for some other scenario, for example, urban macro, LOS, NLOS, outdoor to indoor. So you have to use these parameters. So this code is easy to modify. So you just replace the parameters over here and do the calculations. So here the parameter height of user terminal is 1 meter, height of the base station is 20 meter. The distance between the base station and user equipment is 100 meter, like that. So there is a procedure for calculating delay. So this will give the delay versus channel amplitude. So we'll get this kind of graphs, time delay versus the number of delays at each channel coefficients. So we'll get the boundary profile like this. So these channel coefficients we have to implement in that end-to-end learning code. So there are many parameters, angle of departure, angle of arrival. So this code is for generating one particular link. So finally what you get is so finally you can get the probability profile, the channel coefficients for yeah. So if you want to generate for 200 milliseconds, you can get the like this. So you might have seen the Rayleigh pairing time domain signal. It looks like this only. This will follow relay feeding or rise and feeding. Since it is NLOS, it will be rise and feeding. Sorry, relay feeding. If it is LOS, it will be rise and feeding. So here, if you want to generate the coefficients for, so here I generate for the 200 milliseconds. So if you want to generate for the 100 milliseconds, change the parameter, and sampling rate is given 10 megasamples per second. This is for 100 milliseconds. So you can see that, while designing the system, PyGS system, they decide the frame size according to this one only. You can see that roughly for 1 millisecond or so, it is kind of flat. It's not exactly flat, but it's kind of constant. It's not varying too much. So that we can make one frame size is 1 millisecond. So based on these parameters only, they make it as frame size and everything. So in this code, it's a function of speed also. We can see this, no? V direction. V means direction vector for the user movement. So in this case, you can see the speed also. I'm trying to see the speed parameter. Yeah, we can. I couldn't see it now, so it was there. So if we change the speed, there will be a lot of fluctuations over here. So this channel model we can use it for any application. So this the question is what for radar applications. Oh, so this is specific to cellular communication. So how they made this channel coefficients formula is that they typically they put up one transmitter in the vehicle and go to the field. Or as in the big city, they will move in a vehicle and they put up the transmitter, that is the receiver. So they will measure the received signal strength. They will collect the received signal strength. They will do the curve fitting for path loss and small scale fitting and all. They will do a lot of measurements for cellular structure. So adjusting the transmitter height and the receiver height and everything. For all possible combinations, they will collect the data and do the curve fitting. Based on the curve fitting, they will um, do the uh, uh, extract these parameters. So I'm not aware of any uh, software for radar. So, but I know it for 5G and 6G systems, they use this kind of channel modeling and tools. So some of you asked um, open source tools for channel modeling, right? So there is a Vienna simulator. See this Vienna 5G simulator. It's for university. So we can also use this simulator. Probably it is. So VAENNA, Vienna 5G simulator. So this is what exactly I mentioned. 5G system level simulator, right? This gives list of features and user manual. See this, you can see it over here. Link properties, LOS, NLOS, path loss, predicting cell association, zero Posi equalizer, normal transmission, arc, MIMO, all those things. Interference region, wraparound, macro, pico, femtocells, vehicular, pedestrian, indoor users, movements, buildings, fixtures, everything will be there in this one. So actually, I have not used this one personally. In 2013, 14 like that, we developed our own MATLAB-based simulator for system level analysis. We used to run the code for 1 or 2 days to get some results. We didn't do the full-fledged bit level simulation, but assign our capacity in that kind of simulation we did it. So similar kind of thing they have done it. Probably this is in MATLAB, I guess. Yeah, so they use MATLAB particular version, well, you can check it. So all the details will be given over here. How to install, how to generate the coefficients, all those stuff. So you can see the keywords like urban macro 3D, urban macro 5G. Yeah, you can see refer the manual and do your stuff. Simulator structure is this. See, there are two things. One is link level simulation and the system level simulation. System level simulation means you have a base station. There are hundreds of users communicating. What should be the total capacity? What is the total capacity the system can provide? What is the bandwidth you can use? What is the transit power you have to use? That is system level analysis. Multiple base stations, multiple users. There is one more thing is link level simulator. Link level means there is a one base station, one is equipment. In that link, we have to do the performance analysis, channel coding, all those things. No, you have to use it for link level simulation. So this link level simulation, you have to use it for RIS as well. So the 5G as of now is having base station, diesel equipment, link level simulation, one link. One link, but I mean, two positions, maybe multiple antennas. Maybe the base station have 100 antennas, the user equipment have 80 antennas. Or you can get the correct link and do the calculations. So all kind of MIMO pre-coding, all those things can be done here. When you do the RIS, we have to create your own. You have to modify the code. It's open source code only, I think. We have to use your coding skill to create another RIS module based system. So it's a matter of placing the antenna position, giving the antenna position with the antenna spinning, then change the positions as I mentioned. So as given in this these things, they will be linear simulator also using the same parameters. So it will be exactly the same. It cannot be there will be any slight deviation. So in the link level simulator, you can see. So for RIS, as of now, there is no simulator available in principal standardization. You have to develop your own based on the existing 5G tools. So this is a link level simulator. See this. Yeah, I think they have given added intermediate nodes as well. I guess recently, the version 1.3, they have reconfigurable link services. Intermediate node, as I mentioned, they have already added it. So that is good. In link level simulation, they have done it. So based on that, you can do the turbo coding, TV coding. So turbo coding and all may be difficult to do, but on top of it, you can apply DNN, deep neural network or MLA techniques you can apply. So actually, I haven't checked it previously, but it's shown that reconfigurable service is supported in VNS simulator. Let's see the content here. See, when they talk about 5G simulator, they compare with it to LTE. Similarly, 6G can come to the conclusion. So, reconfigurable. See, NOMO also supported in a simulator. Yeah, series topology base 2 IS. So they are considering two base stations, two RIS units. RIS 1 is controlled by base station 1, RIS 2 is controlled by base station 2. Yeah, so we have to install it and check it how it works. Yeah, they have given the clear steps to how to install and run. See, in the table of contents they have given, right? I think this is GUI based. Link loss metric GUI based. Yeah. Sorry, I have not performed myself. I use Python these days. See this one. So this VNA supports RIS in this. Correct. Simulation methodology. See, for both system level link level simulation, they have user manual, so you can refer. So if you have any doubts, you can contact them. So I know some people are already using this and having some good publications. And there is one more simulator. See you now. See, this is for so only for similar kind of stuff. I don't know whether so this basically involving ray tracing approach. So the one we are doing the Python MATLAB is there is no ray tracing concept. So we use some statistical channel modeling with some distribution for each parameter. But here on top of it, they are using uh, ray tracing. So in this case, you can create a structure, a building structure. We can between the transmitter receiver, you can create structures and see how it behaves differently in the presence and absence of the obstacles, all those things. So as given in the video, no. So we'll be able to. This is open source tool.
Sorry to disturb you. We are at the end of the session. I would like to take one last question, and then I would like
Okay, yeah, sure.
hand over the next session. Sir, how can RIS use it to mitigate line of sight issues in millimeter wave communication?
So what is the issue? Line of sight issue? I'm not getting it. See, millimeter wave
Line
works.
of
So millimeter wave works better best in LOS condition only, right? So you are asking in the absence of LOS how it works.
yes, sir. In the absence of LOS.
Yeah, that's why no. So so this is the example here. So there is obstacle between these two. So it creates some stable link over here. So in this way, we can you get the reflection and with the water. See the wall bend. Typically, if the millimeter wave strike the wall, the EMF wave is absorbed by the wall and all, so it won't be reflected. So if you use a surface like this, it will be without absorbing, it will be reflecting. That is the idea. So this is a simple example. So this is more suitable in case of millimeter wave communication.
Swarnima, you hand over the session.
Thank you so much, sir, for that engaging and insightful session. Also, your hands-on approach was greatly, I think, enhanced our understanding of the topic. Participants' knowledge was all grown, like the hands-on session, like they had a broader knowledge about the topic in the hands-on session. We appreciate your efforts, sir. Thank you so much again.
So if you have, the participants have doubts on how to run and all, they can ask me through my email ID. So they can,
Sure, sir.
yeah.
We'll share them with the email ID, sir.
Yeah.
Thank you so much, sir.
Thank you.